Okay, so good morning, everyone. Am I audible?
Yes, ma'am.
Okay.
Yes, ma'am.
Okay. So hi everyone. Just before we begin, some things to announce. So you all might have got this update on the second assignment. So there was one question in which there was a typo that I'd done like in haste. So there's been a correction on that. So something about the misclassification error. So ensure that you take the latest copy of the assignment. Okay, so that's one thing. And the other thing that I wanted to mention is about the class drive folder. So there have been some issues with the privacy aspects for that folder. So what I'm going to do is maybe sometime tomorrow or so, like I'm going to just revoke access to the class drive folder as such. What I'll do is so many of the content is already visible to you in the form of this kind of material posted. The only difference is for these bigger files, like things like the linear algebra folder. So I will just share that explicitly. So I think I've already done that, but anyway, so tomorrow I'll just revoke access because I didn't want to do it today because many of you might be referring to it to things for the assignment, and it might just cause some disturbance. So that's why I'll do it tomorrow. So just keep an eye out, and in case some material is not available, you can contact Gaurav. So he'll have all the material. Okay. So yeah, that's just something I wanted to tell you about. So we'll begin today's class. So I hope the screen is visible to you all. Right? I think it's shared, right? Okay. Okay. So we were, learning about convexity. We did something about convex sets. So basically, we had these sort of nicely behaved sets wherein any 2 points you take, the line joining them also belongs to the set. Then we also went on to discuss about some aspects of convex functions, and we saw some examples like graphically, and we saw the important feature that any local minimum for these kind of problems where the function is convex and you're trying to minimize it and the constraint set is convex. So for these kind of functions, any local minimum is also a global min. That's what we saw. And we saw some examples of convex sets, hyperplanes, half spaces, and so on. And then we also saw that the set of optimal solutions to this kind of a convex problem is itself a convex set. So we saw it was a simple proof, and some operations which preserve convexity. And in the last class we were doing Jensen's inequality, which is just an extension of the definition of convex functions to infinite dimensions. Okay, so and we were looking at some characterization of convex functions. So one was a first order condition. So these are some ways you can use to check whether convexity actually holds for a given function. So we saw a first order condition, and we said that the function always lies above the approximation. Okay, about the first order Taylor series approximation. So there's one point I wanted to clarify. This is based on a follow-up question from one of you guys. I think it was Vipul. So it's a valid thing that he asked. So like in doesn't the line shouldn't the line always lie above the function? So there are two lines here that we looked at. So one thing was the definition of convex functions. Okay, so where we said that the line joining any 2 points. Okay, so if you take x fx and y fy, so the line joining these points lies above the curve. That is one characterization we saw. Okay, now the other one, what I talked of subsequently, was the approximation. So this line that I'm talking of here is not the line joining any 2 points of the curve. It's rather the first order approximation at any given point. So, and by now, I think the first assignment asked you to construct the Taylor series approximation, right? So here what we are talking of is the first order approximation to the curve at this point x. Okay, so the function will always lie above this approximation. Okay, and that's going to be true for any point you take. Okay, so it's sort of like these two lines are different. So I hope there's no confusion about what lines we are talking of here. Okay, so yeah, so I just wanted to clarify that. And then finally, what we did was we stopped at this point where we looked at a second order condition. So where we said that, if a function is convex, then we have that the Hessian at every point you take, the Hessian has to be positive semi-definite. Okay, and so this is an if and only if. So if it is convex, then this condition is true for every point, and similarly, if this condition holds for every point, then the function is convex. Okay, and so in one dimensions, what this just meant was that the second derivative is greater than or equal to 0 at every point. What it meant intuitively is that the slope is just increasing at every, as you go on, the slope just increases. So these are sort of some of the characterizations we saw. And I also want to just add that, if you're looking at concave functions, okay, so where the shape is kind of reversed, where you have like some function like this form. Okay, uh, so for these kind of functions, for concave functions, all the inequalities are just going to reverse, right? So we saw that for the first order condition, you have the approximation lies above like this. The first order approximation will lie above the curve. And similarly, now for the second order condition, you will have that this Hessian is going to be negative semi-definite at every point. Okay, so it's just some symmetric conditions like this, which you can derive for concavity as well. Okay, so were there any questions till now? With the material covered so far, I hope things are all clear. Okay, so maybe let's move on to some examples now. So we only saw some examples visually, so let's just take some functional forms. So first example is this function e power ax for any a you take. Okay, so this is a convex function. Okay, so how you can do it is you take, this condition helps you, right? The second derivative. So if you take the first derivative, what do you get? What's the derivative of this?
AEX.
A e power ax, right? Okay, and the second derivative is going to be what?
A square EAX.
Okay, a square e power ax. So this is going to be greater than or equal to 0 always, right? So that's why it's a convex function. You could also try to verify this using the definition itself. Okay, so there are different ways to show this. Now another example is consider the function log x. Okay, where x is greater than 0. So what is this function, convex or concave? That's what we want to
Concave.
answer. Yeah, this is a concave function. So how you can see this is you can use the same way. So f dash x is what?
1 by x.
1 by x, and f
Minus 1 by x square.
minus 1 by x square. So this is always going to be less than 0. Okay. So that's why this is a concave function. Now, so you can try this out for any function you get. The way you show something is convex or concave is by checking one of these conditions. So you could check the other equivalent conditions. For example, the first order conditions is also something you could just verify and see whether even that concludes the same. Okay, they're all equivalent. Now another example is norms. Okay, so all these norms are convex functions. So it just holds because of the triangle inequality. Okay, so yeah, that's one thing. And now another thing is max of coordinates. So f of x, if you define it as max of x1 to xn, okay, so then even this is a convex function. Okay, so the proof is actually just follows from the definition. So you what you could do is you take the max of this. So this is the one you have, f of lambda x plus 1 minus lambda y. You want to see if this is less than lambda fx plus 1 minus lambda fy. You want to compare it against the two, against this one. So you want to check if this is true. So what you can do is, if you take this max over each of the coordinates, okay. So this is a joint term, and if you split these, the summations, you're going to get something even bigger. Okay, so that's why this inequality holds true. Okay, and so hence this convexity um, follows as a result of that. Okay, now another thing is functions of this form. F of x is summation ci xi. So these are actually linear or affine functions, you could call it, and these are actually both convex as well as concave. Okay, so these are the ones that follow both ways, both side inequalities, and it turns out that these are the only functions for which it's both convex as well as concave. Okay, any other function you'll have it either convex or concave, or even neither. Okay, so yeah, so these were some examples I just wanted to showcase. And there are so many examples of convex functions, and you're encouraged to go through the Boyd book for all these examples. So in general, like we did for convex sets, okay, so there are some operations which will preserve convexity, so that helps you conclude even faster whether some function is convex. Okay, so so that is applicable here too. Like in the earlier case, we saw about convex sets, and now we'll see with functions. So this is not an exhaustive list, but just to give some idea about it. So if two functions are convex, the sum is also going to be a convex function, and of course the by default you should have that it's defined on the same domain. Otherwise, it doesn't make sense to add these functions. Okay, so you should verify that the definitions hold through here too. Okay, so that's about adding two functions. Now, another operation, which is, this is an important one, it gets used in many places. Like even later, you will see things like the dual optimization problem and stuff. So there also you will have this kind of max of functions. Okay, so it turns out that max of these functions is always going to be a convex function. So intuitively, if you just see it in terms of a picture, so it's something like this. F1 is this one, and say F2 is something like this. Okay, so the max of these two functions, so this is on this whole real domain. So the max is this function, right? So this one here. Okay, the max of these two. So this is also going to be a convex function. Okay, you could also prove it using these other methods we did. And on another note, if you have minimum of these concave functions, that's also going to be a concave function. Okay, so that's about these. And now, if you have exponential function, right? If exponential of g of x with g of x as convex, so this is also going to be a convex function. Okay, so maybe what we could do is, yeah, I think it follows from the second order conditions, right? So if you take f dash of x, you're going to just get what? So what are you going to get? You're going to get e power g of x times
E.
g prime, right? Yeah, the first derivative. Okay. Now the second derivative is just going to be what is it going to be?
Exponential gx g dash x plus
Right. Plus
exponential gx g dash x
exponential gx times this. Okay. Okay. So now, yeah, now we need to say that this is greater than 0, right? So this quantity is going to be greater than
G
0
prime x
always.
square.
This is g prime x square, right? Okay. Yeah, thanks for pointing this out. So yeah, now we see that these two terms are going to be always greater than or equal to 0. So that's where this holds. Okay. So that's about some operations. Okay. So it's yeah, there are many more operations out there which talk to you about when convexity is preserved. So this is for you all to read further and understand it. Okay. So with this, I will just move on to some other concepts which connect convex functions and convex sets. Okay, so this is the first one. First of these is what is called the epigraph of a function. Okay, now this also gives another helps to give another characterization of convex functions. So the epigraph is an object which you define in one dimension higher than the function itself. So what I mean by this is if you have f as a function from Rn to R, okay, now so that's this line here, this function, it's another line, the curve. Now the epigraph is basically an object. It's this whole space. It's in this n dimensions plus one. Okay, so here in this case that I'm showing you, it's just a two-dimensional object. So it consists of all these points x, t, okay, such that f of x is less than or equal to t. So basically all the points which lie above the function. Okay, so it's a graph of this function and everything which lies above this function. So this one in red, that's the epigraph. Okay, it's the region above f. Okay, so you can see that it's a subset of Rn plus 1. Okay, and one important thing is if f is a convex function, and if f is a convex function, you have that this set epigraph is a set, right? And that is a convex set. Okay, and similarly, if epigraph is a convex set, you have that the function f has to be convex. Okay, so this kind of connects the two notions. You have convex sets, you have convex functions. Of course the name is similar and you also have a similar definition, but other than that, is there something which binds these two? Okay, and it's always like it feels that there must be something, right? Because the definitions are so similar. And so epigraph is one such thing which has a direct connection with these two concepts. Okay, so this is also another way you could use to check if a function is convex. You just check if the epigraph is a convex set. Yeah, so it's not in all these operations you don't know which one will help more, because even checking if a function is if a set is convex, that also may not be easy always. So the way to do is you just try these different techniques. Okay, so now another concept which connects the two is something called these alpha sublevel sets. So this is just looking at a function you have like this, and you cut off some threshold like this alpha. Okay, so now the set S is just the set of all points for which f of x is less than or equal to alpha. So if this is the value of the function at which you want to threshold, so this is the first point for which f of x is less than alpha, less than or equal to alpha, and basically you have this whole interval. Okay, so for everything in this set, so this is the set S alpha basically. So for every point in the set, you have that the function lies below alpha. So it turns out that if a function is convex, then all its sublevel sets. So this is a sublevel set for a particular value of alpha. So if a function is convex, then for every alpha, you have the sublevel set is convex. Okay, so the proof, it's just again by the definitions. So if you take any x, y in S alpha, so you have that this f of lambda x plus 1 minus lambda y. Okay, it's less than lambda fx plus 1 minus lambda y. This is just the definition of a convex function. This is because the function is convex. So now this is just going to be because f of x is less than alpha, because x lies in this set S alpha. So this is less than lambda alpha, and this is also less than alpha. So this whole thing is going to be less than 1 minus lambda times alpha. So this is in turn equal to alpha. So that's why any point you take, with any line joining these xy's also will lie in the set as alpha. Okay. So yeah, so remember that this is it's only one-sided. If a function is convex, then all its sublevel sets are convex. But the other way, it's not true. Okay, so that's something you should remember. And there are examples of this, and these kind of functions with all its sublevel sets convex, those are referred to as quasi-convex functions. So quasi-convex function is a function for where all its sublevel sets are convex. Okay, function with all sublevel sets convex. Okay, so this is not necessarily a convex, the function is not necessarily convex if this happens. And an example for this is you can take f of x as x cube. Okay, so so you can verify that it's actually all the sublevel sets are convex, but the function is not convex itself. Okay, so any questions still here? Okay, so it's clear to Rohit. What about all of you? The simple notions, but I just want to ensure that you're all with me. Is this fine? Please, you can respond in the chat box. It's clear. Clear. Okay. All right. Okay. Good. So now, I want to talk to you a little bit about these convex hulls. So we briefly mentioned this in the initial time when I talked to you about convex sets. We define this convex hull. Basically, it's the smallest convex set which contains the set S. Okay, so you can have a non-convex set. So something like something like this. If the set S is this, then the convex hull is basically obtained by filling in these parts, the red part. So what I mean is that the set originally that I looked at was this whole thing. Okay, in the interior as well as the boundaries. Now, if the non-convexity is arising because of these portions, and if I add in this part as well, all these regions as well, then the set becomes convex. So the convex hull is this whole region S, and along with these points here. Okay, so that's the smallest convex set which contains S. Now, if S was originally convex itself, then the convex hull is just itself. Okay, so you represent the convex hull as this set of all possible convex combinations of the points in the set S. Okay, so you recall that this means that it's a convex combination. With the lambda is greater than 0, and if they sum to 1, that's a convex combination. And basically, the convex hull contains every convex combination of all its points. Okay, so this should be true for every value of n. Okay, so to be more precise. So now, a very important theorem is this Caratheodory's theorem, which says that if you take any set and you look at its convex hull, okay, and then any point you take in this convex hull, of course, you should be able to write them as a convex combination of many points. Okay, but the interesting thing is that you can write it as a convex combination of n plus 1 points. So the set is a subset of Rn. Okay, and so you don't need to take more than n plus 1 points. So n plus 1 points is sufficient to express every point in this convex hull. Okay, so that's the statement of this Caratheodory's theorem. So is the statement clear? The main thing is about this n plus 1 points. You can write it as a combination of these n plus 1 points, and nothing more than that is needed. Okay. So I hope the statement is clear. So please stop me if not. Okay, so the proof is important. The ideas of this theorem, the proof of this theorem, it turns out that it comes up everywhere. Like later when we do linear programs, also this kind of the nature of this proof is going to show up. So that's why I thought it's important to discuss this proof in class. So let's just look at the proof. So, but before that, I just want to check with you all, is the statement clear? Like you're following, right? What the Caratheodory theorem states? Any questions on this or any confusions on what the statement is about? It's clear. Okay. Okay. Fine. So just stop me if it's not clear. So I'll just start with the proof. So what we are trying to say is, if any point you take, you want to see what is the convex combination, right? That gives this point. So you take any x in this convex hull, and say x can be written as this convex combination of the points y1 to yn. Okay, so there are m points, and you've been able to write it as a convex combination of them. This is anyway true. You can write this because it's in the convex hull. So by definition, there are going to be some points where you can write this. Okay, and so summation of these alpha i's is 1, and all of them are non-negative. Okay, so now the question is, how many of these m's are you going to take? Okay, so if already you have that m is less than or equal to n plus 1, then it's done, right? So we already have a representation for this point. So suppose not, okay? So if m is greater than n plus 1, so you wrote this as more than n plus 1 points were, the representation had more than n plus 1 points. So the way this is going to work is that you will, it turns out that all of them are not important, and you will show that, at least one of them is redundant. Okay, and so you keep doing this. So whenever you have more than n plus 1 points in the representation, you keep eliminating 1 point by 1 point till you come to n plus 1 points. Okay, so it's kind of an inductive proof in some sense. Okay, so for this, what we have in our tool to capture this notion of redundancy is the idea of linear combinations. Okay, so we'll try to see whether this system, okay, the summation beta I yi, so yi's are all vectors in Rn, and you want to see if this summation equals 0 with all the beta is, with this sum equal to 0. You want to see the solution to this system. Okay, so basically you want to check for the betas, find the betas here. Okay, so these betas are the variables and y's are given, and you want to see whether the betas, there's something other than 0. Of course 0 satisfies these equations, but is there something other than 0 which which satisfies these equations? Okay, so that's what we will do. So now you can in turn write this as in this form, right? In the matrix form, where the y's are all in n dimensions. Okay, and so you have n of these, and you remember the the linear combinations, right? So you take beta 1 times y1, beta 2 times y2, and so on, plus beta m times ym, that should give you 0. Now you can add also one more row here. Okay, so which says that, beta 1 times 1, beta 2 times 1, plus so on up to beta m times 1 is 0. Okay, so this is a system in n plus 1. There are n plus 1. Sorry, the dimension is n plus 1. So I think I made some mistake while writing this. Did I? Okay, so just give me a second. Okay, I probably might have made a mistake. Times this one. So you should probably have it here, right? So 1 times this. And so, okay. So what are we going to get if we write this? This is going to be beta 1 times y1 1. Yeah, okay, I think it's fine. Beta 2 times y2 1 plus so on plus beta m times y m1, right? Yeah, okay, I think it's right. So this is going to give you just 0, right? So yeah, I think this is right. Okay, so so basically what you have here is an n plus 1 dimension, I mean n plus 1 rows and m columns. Okay, and this is a system with the m, we assume that m is greater than n plus 1. Okay, so that means there are, it's a wide system. Okay, so there are many, this dimension is more. Okay, and so definitely there has to be a null space here. Okay, so the null space is non-empty. So by that what we mean is that there is some betas which are not all 0, such that this expression is satisfied. Okay, so so if you can just take some of those betas, and so you will so the idea is to basically use these non-zero betas which give this which satisfy these equations. And now you remember that you also had this representation, right? X is summation alpha I times yi. Okay, so what you can do is, you can just construct another point, which is this alpha I minus epsilon beta I for some value of epsilon, which we will see. Okay, so basically you're trying to remove one of the points by doing this. Okay, so that, one of the alpha I minus epsilon beta is 0. Okay, so one thing to note here is that, if not all the betas are 0, so that means there is at least one beta which is greater than 0. Okay, so there must be at least one positive, and of course you'll have something which is negative also, because you need to have this summation as 0. Okay, so out of all the betas which are greater than 0, you just take the minimum value here. Okay, so the reason why you do this is when you construct a new point. So this is a new point that you're constructing, and you want these ones, this alpha minus epsilon beta, is you want these to be greater than 0. Okay, and you also want it to sum to 1, because that is the convex combination that you desire. Okay, so that's why you you look at all these which are greater than 0. Okay, and so you look at the minimum value of this alpha minus beta I. So for the I for which this is minimum, what's going to happen is this quantity alpha minus epsilon beta I, that's going to be 0. And for everything else, it's going to give you some value which is greater than 0. Okay, so so in that effect, what you have done is that, for some k, so let there be some k such that alpha k by beta k is the value of epsilon. Okay, so for that k, this alpha k minus epsilon beta k, this is going to be 0. Okay, and so what you have done is you have just eliminated one point in some sense, right? This is the same point x, so this is actually x itself. Okay, so that we'll just see that now. So it's the same point, but when one of the components has been removed. Okay, so why is this the same as x? That's because you still have this same thing, right? Summation alpha minus epsilon beta is 1. Okay, because yeah, that's because of the way we have set the epsilons. Okay, and this is still x tilde because of the betas were chosen such that it satisfies this expression. Okay, so if you take this term, right, let's say, so alpha I minus epsilon beta I times yi, this is what you wanted to take. Okay, so this was summation alpha yi. So this was what we started off as x. Okay, and minus epsilon times summation beta yi, and this is actually 0. Okay, so that's why this x hat that was constructed in this way is exactly equal to x itself. Okay, so what we got now is a representation using y1 y2 and so on up to yk minus 1. And yk had a coefficient of 0, so that was, we don't consider that. And then you took yk plus 1 and so on up to yn. Okay, so this has 1 point less than your original representation. So yeah, so that's, you keep doing this till you basically reach n plus 1 and then you're done. Okay, so was this clear? Are there any questions on this? Okay, you're all quiet now. So are there any steps which are not clear to you? Okay, so let me ask someone. Maybe Siddharth Solanki.
Ma'am, I was just thinking, why will this construction not work when we have exactly n plus 1 things? N plus 1
When you,
components.
so when you have exactly n plus 1 components, you're already done, right? Oh, you're saying like, why can't we do lesser than n plus 1 points?
Yes, ma'am. I was just thinking on that.
Okay.
No confusion as such, but I was.
Okay. Yeah. So yeah, if you have if you use only less than n plus 1 points, perhaps you may not be able to cover the entire range of these points. So that's perhaps why it could fail. Okay. Yeah, maybe a way to do that is by taking some examples and seeing where it fails. Okay, because the dimension of this set is going to be exactly n. Okay, but I mean, if you look at it as this is not a subspace, but if you had it as a subspace, you could write it in in terms of a linear combination of endpoints. But now this is a convex combination, so you need to do something more here because you need to have this condition. So yeah, a way to do it is probably try some examples out. But okay, so but with these sequence of steps, is it clear to you like what's going on?
Yes, ma'am.
This is clear. Okay. So what about the others? Devansh?
Yes, ma'am, it's clear.
It's clear. Okay. Good. So what about? Let me
Ma'am,
ask. Yes,
I have a doubt.
Nitish. Yes,
Ma'am,
Nitish.
we proved that we need only n plus one these of x's to represent the entire set. But did we say that if m is less than n plus one, then it is still fine?
Yeah, so the claim is that you need n plus 1 points, but I mean at max n plus 1 points. Okay, so as maybe I should add that here, at max at n plus 1 points. That's what the idea is. Okay, so yeah, you can have still less than n plus 1 points. That's okay, right?
Okay, ma'am. Okay, ma'am. Yeah.
Yeah, maybe I should have made it a little more clear. Yeah. Thanks, Nitish. That clarifies something. So, what about the others? Let me ask some master's students, maybe Lakshmi. Lakshmi is a PhD student, I guess. Lakshmi, is it clear to you?
Yes, ma'am.
Okay. What about others? Tushar?
Yes, ma'am.
Tushar is clear. Okay, good. Sanila?
Yes, ma'am. It's clear.
Okay. Okay, good. So yeah, so these proof ideas, like about eliminating one point, that will show up later, like when we do the simplex algorithm. So that's for solving linear programs. That's a well-known technique, and so that's why I thought this proof. I mean, the idea is similar to what is done in the proof of Caratheodory's theorem. So that's why I thought it's useful to go over this. Okay, so yeah. So now what we saw was about convex hulls, and what is the use of doing this convex hulls? Okay, you represent the set as a convex function. Okay, so is there somewhere else that we can use it? What is the implications? Okay, so to see that, one consequence of these convex hulls is that if you have an optimization problem where the objective is linear, okay, and the set is not necessarily convex, the set S is not convex, but it turns out that if you write instead of taking the set S, if you take the convex hull of S and you try to minimize the same linear function. Okay, so these two are going to be equivalent. So what I mean is that the objective value, the optimal value of this function, this optimization problem, and the optimal value you get from here, it's going to give you the same value. Okay, so it's not immediately like, okay, if you have this convex hull, it's not necessarily that it makes it simpler. Okay, but in some cases the convex hull, this set might be non-convex, but when you take the convex hull, in some cases there are some nice representations that you have. Okay, so in that case you can solve this problem more efficiently than you would than you could solve this. Okay, so some examples of this will be there. You can find them in integer programs. Okay, because we just saw the polytope with the integer points of a polytope. If you take that is a non-convex region. Okay, so this set is going to be non-convex, but when you take the convex hull, I mean, for some cases, not all integer programs, but for some cases, this has a nice, I mean, you can represent these with just linear inequalities. Okay, so what you're going to get is a linear program in that sense, and linear programs are efficiently solvable. Okay, so that's the utility of these convex hulls. Okay, so let's just see a small proof of this. It's a simple proof. So now I want you to answer this. Of the two sets, S and the convex hull of S, right? So which is a larger set, right? Of course, the answer is already there. But yeah, the larger set is just the convex hull of S, right? Because it's a smallest set which contains S. So S is a subset of this convex hull. Okay. So now if you're trying to minimize a function f of x over the set S versus this convex hull. Okay, so this has more number of points. Okay, so you will at least get this objective when you try to minimize over the convex hull. Okay, but now there are more additional points here, so you will maybe there's a hope of getting an even lesser value. Okay, since you're doing a minimization, so that's why this is true. Okay, so if you minimize the function over the set S, you will be not, I mean, you'll get a lower value when you try to minimize over the convex hull. So what about for maximization? Can someone tell me what happens? So suppose I do max of f of x over x in S and max fx for x in convex hull. So which way is it going to be? Is it going to be this way, or is it going to be, which is greater?
And for convex hull, it should be greater.
This should be greater, right? Because this is a larger set. So by the same logic, I mean, if you you have more points in this convex hull, so you can perhaps get a bigger value here. Okay, so this was just to make the idea clearer. So this because okay, so these were the two values we were looking at this problem. So we know that this is anyway going to be true. So now what we have to see if whether the other way is also true. So whether the minimum value of this fx over the convex hull, whether that's also going to be less than minimum value of f of x. I mean, whether it's going to be greater than fx for the case of this linear functions. If that is the case, then we are done. Okay. So yeah, basically what we want to show is this. Okay. So now since this is a linear function, and let us say that there's some x tilde, okay, from this convex hull, which minimizes this linear function. Okay, So you know from Caratheodory's theorem that this x tilde can be written as a convex combination of n plus 1 points. Okay, so yeah, at least not more than n plus 1 points. Okay, so this is something that you can write. So these yj's are all belonging to S. Sorry, this has to be in. This is all in. Yeah, all in S, right? Because this is from the Caratheodory's theorem. So all these yj's belong to S. Okay, so let's just write that. So this function f is just summation ci x tilde, and x tilde is just this. Okay, now what you can have is, you can just interchange these summations, so it still doesn't change the value. Okay, now what you have here is, okay, some weighted term ci times some point. Now for each of these points yj, if you take ci times yji, okay, so this is actually ci c transpose yj. Okay, so this is actually a lower bound for this is the minimum value of the same value from the function z, from the function s, sorry. So C transpose Yj, because Yj belongs to S, okay, a lower bound for this is the minimum value of C transpose Z for where Z, this Z belongs to this set S. Okay, so that's why this is true. So for every point here, for every j, you just do this. Okay, you replace this by the minimum value. So that's why you have this greater than or equal to. Okay, so now this is a convex combination, right? These lambdas were a convex combination. So you had summation lambda j is 1 and lambda j is greater than or equal to 0. Okay, so that's why this is 1. So what you get is this whole term here is just the min value over S. Okay, so what we've shown is the other way inequality is also true. Okay, so that's why you have that these two are equivalent. Okay, so yeah, I hope this is clear to you all. So this is a very useful property in general where you can focus on the convex hull. Okay, now another thing which helps us to see convex the utility of these convex hulls is to see analyze about convex problems. Okay, these kind of of maximizing of convex function, sorry, minimizing a convex function over a convex set. Okay, so is this always going to be an easy problem? Right, so there is this traditional belief that convex problems are all easy, and the moment you identify that a problem is convex, then yeah, it's all done. But actually that's a misnomer. It's not always the case. Okay, of course there are some convex problems. I mean, there's a good class of convex problems which can be solved efficiently, but this is not always true. Okay, and these convex hulls help us to see this. Okay, so for that you can take this take any optimization problem. Okay, so this is any arbitrary optimization problem you take. Okay, so by now we know that not all optimization problems are easy. So this could be an NP hard problem itself. Okay, so now this you can write it alternatively in this way. Okay, you can formulate it this way. You want to find the smallest value which is greater than or equal to fx. Okay, so this is an equivalent representation, right? So you take x in omega and yeah, the smallest one less than, I mean smallest value t, which is greater than or equal to fx. So now the variables here are t and x. Okay, so both these are variables. Okay, so this is now linear, right? The objective is a linear function of the variables because it's just t. Okay, so now what you could do here is again write this as a convex hull. Okay, so we just saw now that if you have a linear optimization problem over a set, you can replace the set with its convex hull. Okay, so now this is just equivalent to saying minimize t over this convex hull. Okay, so this is what, it's linear and this is a convex hull, and this is a convex set. Okay, and this function is linear, and I mean it's also convex. A linear function is also convex. So yeah, so if all convex problems were easy, then this could be solved easily. And so this, if this was an NP-hard problem, you have an easy solution to it. Okay, so there's something wrong here, right? So just writing this as a convex hull representation doesn't make the problem easier. That we've just seen that. So that's the idea. That not all optimized convex problems are easy, and this convex hull representation helps us to see this. Okay, so yeah, so this is the idea that I wanted you all to carry with you on these convex hull representations. And yeah, so in the literature, what people do is, when they say convex optimization problem, they usually refer to some problem like this. I mean, of course, it's a convex problem, but they additionally focus on these kind of constraints. Okay, so minimize fx with some the inequalities and the equalities written in this way, where all these are convex functions. The g's are convex and h is convex, so h has to be linear. Okay, so this is the way, this is a subset of convex problems actually, but traditionally this is the representation that people use to write convex optimization problems. And even in many of these solvers, it will expect the formulations to be given this way. Okay, so when people study convex optimization problems, they usually study these kind of problems for which the analysis is a little more straightforward. Okay, so now one thing is, okay, I hope I'm still connected. Are you all able to hear me?
Yes, ma'am.
Yes, ma'am.
Okay, okay. So the power just went. I was just wondering whether I got disconnected. Okay, all right. So just to wind up here, it doesn't mean that if omega is a convex set, okay, it doesn't mean that these representations have to be convex. Okay, so for example, if you take this kind of a region, okay, so these are two non-convex regions, but the intersection of them, so these could be one inequality, so this could be gi. So again, I'm meaning the whole region enclosed here. Okay, so not the boundary alone. Okay, so this could be one function and this could be another function. Okay, so an intersection of these is a convex set. Okay, but these themselves are not convex. Okay, so these functions g's are themselves not convex. Okay, so yeah, so another example is this set omega, where this is actually written as a non-convex representation. Okay, but if you take this set of the real line where x cube is less than or equal to 0, it's just this part, right? So this is x, and so basically this part. Okay, sorry, but this function x cube is not a convex function. Okay, so now if you wrote it as x less than 0, that was okay. Okay, so yeah, so these are just some minor points, but something that you need to pay attention to. Okay, yeah, so I think with this I will stop this class. I think we are running out of time. So if you have any questions, I'll hold back and answer. Otherwise, thanks a lot for making it in the morning. I'll see you on Thursday.
Thank you, ma'am.
Thanks.
Ma'am, for the equivalent representation of a convex problem,